jump into we'll just get rid of that. So today we move on to part 2 of our discussion of AGN. So just to begin, we'll just recap what we talked about last time. So last time we kind of looked at multi-wavelength observations of AGN, but with a real focus on the X-ray component of that. And we saw how we can piece together the structure of that central engine that's powered by material falling into a supermassive black hole in the center of a galaxy. We talked about how the material falling into the black hole forms a flattened accretion disk, or at least it's a flattened accretion disk if our mass supply rate is within the right sort of range, if the mass supply rate isn't too low and it isn't too high. We talked a little bit about a jet, and we also talked about this mysterious structure that we call the corona. This region of high energy accelerated particles close to the black hole that we know must exist because it's producing the bright X-ray continuum emission that we see. Also bright X-ray continuum that shines down onto the accretion disk and reflects. But we don't know how that corona's formed. We think it's got something to do with the interaction of the magnetic fields, both magnetic fields going through the black hole itself, getting twisted up by the spin of the black hole, and the magnetic fields associated with the accretion disk that also get twisted up as the material orbits round in the disk. But there are different forms that corona could potentially take. It could be heated by the magnetic fields from the disk itself and produce a hot layer of material on top of the accretion disk that we see X-ray emission from. It could be particle acceleration that's happening at the base of the jet, that's dissipating energy and releasing the X-rays that we see. Or it could also be a failed jet. In the radio quiet AGN, we see particularly strong coronal emission from close to the black hole. And it's possible that the energy that would have gone into launching the jet is getting dissipated into this small region around the black hole. We also talked a little bit about winds and outflows, in particular those mildly relativistic ultra-fast outflows that carry enough energy and momentum out into their host galaxy that they could be one of the pathways, in addition to the jets and the radiation, that AGN interact with their environments and they help govern the structure we see in our universe, a process that we call AGN feedback. So today we're going to zoom in right on the very central region of our AGN. We're going to talk about how we can use X-ray observations to map out what's happening right outside the event horizon of the black hole, to learn more about what's happening in the inner parts of the accretion disk, and maybe try and get some clues about that mysterious corona. With 2 different techniques that we've been working on for the last few years, using X-ray reflection and a related technique in the time domain using X-ray reverberation. We'll talk about how we can measure fundamental properties of the black hole using these techniques. I'll give a brief introduction to how we can measure the spin of a black hole. And if we have time, I'll talk a little bit about how we can measure the mass of a black hole, but most of those measurements aren't done in the X-ray range. They're done mostly with optical data. And then we'll talk about a little bit about how we can get clues about how these supermassive black holes formed in the first place. So X-ray reflection. We have our accretion disk of material in orbit around our black hole, and we have this corona that's producing X-rays. We talked about last time how this corona shines down onto the accretion disk. The plasma in the accretion disk reprocesses those X-rays by a number of different physical processes. There's Compton scattering, there's heating of the disk, there's the Bremsstrahlung emission that results from that. There's photoelectric absorption in the atoms and the ions within the accretion disk. And then importantly for our discussion today, after that photoelectric absorption, the atoms and ions in the disk can emit fluorescent lines. In particular, we have the iron K line. If we had a piece of iron in the lab and we shone X-rays onto it, we'd see this K line coming out at an energy of 6.4 keV if it's neutral ion, slightly higher energies if it's highly ionized ion. But the combination of the Doppler shifts and the gravitational field of our black hole shift the energy of those line photons that we observe. So that means what starts as a narrow emission line gets broadened into this characteristic shape that indicates we've got reflection from an accretion disk right outside a black hole. So we have a blue shifted peak on our emission line just above 6.4 keV, and then we have this broad red shifted wing of the line. And these are the line photons that are being produced in the very inner radii of the accretion disk. And I should say this isn't a simulation, this is a real iron K line. This is from XMM Newton observations of a Seyfert galaxy called IRAS 13224. So how exactly does that broad emission line get produced? Well, imagine we've got this accretion disk, a flat accretion disk that's going in orbit around the black hole. Ignoring general relativity to begin with, just thinking about classical Newtonian physics, we've got one side of the disk coming towards us, one side of the disk moving away from us. So what starts as a narrow line at 6.4 keV, so here 1.0 means this is the ratio of the energy we observe to the energy that the line was emitted. This line gets split into this double peaked profile. We have a red shifted side from the side of the disk that's moving away from us, a blue shifted side from the line from the disk that's moving towards us, and then from the bit of the disk that's moving transverse to our line of sight. In classical physics, we don't expect there to be a Doppler shift there. However, if instead of using classical physics to calculate our Doppler shift, if we use special relativity, which becomes important because at our innermost stable orbit around the black hole, the orbital velocity is half the speed of light. So we can't use a classical Doppler shift formula here. We need to use the special relativistic Doppler shift formula. We have two additional effects. The first one is the transverse Doppler shift, material that's traveling even perpendicular to our line of sight. Because it's moving relative to us, its clock ticks more slowly than our clock. So what it thinks is a high frequency wave. Because its clock is running more slowly than us, we will measure that as a lower frequency wave. And this gives us what's called the transverse Doppler shift. So we can see that relative to the classical Doppler shift, our entire line profile shifts to the left here. There's a second effect in special relativity, and this is the effect of relativistic beaming. If I have something moving towards you, the aberration of the angles as measured by the emitter and by us means that if we have something moving towards us, the light it emits, even though this material thinks it's emitting its light equally in all directions, we will measure that light being emitted preferentially in the forward direction of motion. So the blue shifted side of the line appears brighter than the red shifted line because the blue shifted emission gets beamed in our direction, the red shifted side of the line gets beamed away from us. So that's just special relativity. But then we need to include the effects of general relativity because we're now right outside a black hole in the strong gravitational field. There are two different things that happen in general relativity that we need to worry about. The first one is gravitational redshift. As a photon climbs out of a gravitational potential, it will lose energy, or we will measure it to have lost energy. So what starts as a 6.4 keV photon, even from stationary material, will be shifted to lower energy by the time it gets to us. But that gravitational redshift changes as a function of distance from the black hole. So the photons that are emitted closest to the black hole are gravitationally redshifted to lower energies than those photons that are emitted further from the black hole. So what we see here is that this is a simulation of an accretion disk. If ever we had an infinite resolution X-ray telescope and we can actually resolve the iron K line coming from the disk, this shows the blue shifted emission, the emission that's unshifted, and then the red shifted emission in the blue and the red colors here. And we can see that actually this is asymmetric. We see the blue shift on the side of the disk that's moving away from us, towards us, but it's not just the side of the disk that's moving away from us that's redshifted, it's everything that's close to the black hole. And this takes this double peaked line profile we get from special relativity and smears it out with this extended redshifted wing, as we put in the gravitational redshift from all the different radii. And then the last thing that happens is gravitational light bending. Photons emitted close to a black hole will be focused towards the black hole. So our black hole here acts as a gravitational lens. So classically, this image here should look like a flat disk. We have the event horizon of the black hole in the middle, and then there should be a shadow of the event horizon on the backside of the disk. There should be part of the disk that's hidden behind the black hole, because light can't travel through the black hole to get to us. However, the light that's emitted from the backside of the accretion disk gets emitted. It can be emitted traveling upwards away from the black hole, but then the gravitational field of the black hole will then bend that light towards us. So what we see is an image of the backside of the accretion disk, the bit of the disk that should be hidden behind the black hole. We actually see this above the black hole. And this would be kind of like me standing here. My feet are hidden behind this bench, as far as you're concerned. But this would be like you being able to see my feet, because the light from them is bent around the bench towards you. And we can visualize the way this light bending works. So these are some other simulations I ran of how light travels in the curved space-time around the black hole. So if we have a corona that's sitting somewhere above a black hole, so imagine here this is either a jet base or a failed jet, it's emitting X-rays. The gravitational field of the black hole grabs these rays, and instead of them traveling in straight lines, they get bent down to the inner parts of the accretion disk. And this is important for us because if we have a corona close to the black hole, we get a lot of X-rays bent onto the inner accretion disk. So this means our inner accretion disk is very strongly illuminated. We get a lot of X-rays reflected from the very inner parts of the accretion disk. And then, as I just said, we have that light bending between the disk and us as well. And you can see here, so in this picture, if I just change my pointer here to a dot, in this picture, our telescope is somewhere up here. We have the rays from the near side of the disk that kind of travel straight to us, but then the rays from the back side of the disk, you can see here how each of these rays is picked up around the black hole. And another cool feature here is our black hole is spinning, and you can see when the black hole is spinning, how these photons get pulled round in circular orbits around the black hole. So these photons can actually go round the black hole many times before they come out to us. So how can we use this reflection from the inner accretion disk to measure the spin of our black holes? And Jack's going to talk more about this later, I believe, but this will be kind of an introduction to this. And I think it's good that we talk about it twice, because this is quite an important concept in both stellar mass black hole and supermassive black hole studies. So we remember in general relativity, there's this innermost stable circular orbit. We can't stay in a circular orbit at a radius below the ISCO. So that means our accretion disk should remain dense up until the innermost stable orbit. But then once it gets to the innermost stable orbit, the density of the disk will drop as the material starts falling rapidly into the black hole. So we should only really be seeing reflection and strong line emission from outside the innermost stable orbit. We shouldn't be getting strong line emission from inside. So this is kind of illustrated here. So the blue line here, this is a stable orbit around a non-spinning black hole at 10 gravitational radii. So you can see this blue line can just keep going around the black hole. But now if we try and have an orbit at 6 gravitational radii on a non-spinning black hole, so this is the innermost stable orbit, we put something in orbit at 6 RG and then we give it a little push, You can see it manages to do a few spirals around the black hole, but then it transitions onto this plunging orbit. And you can see how quickly it spirals in. It doesn't do many turns in the inner radii. It just falls, I mean, pretty much from kind of 5 RG or so, it just falls straight into the black hole here. But the location of this innermost stable orbit depends on the spin of the black hole. So in the case that we're trying to orbit in the same direction as the black hole spin, the innermost stable orbit follows the blue line here. So it goes from 6 RG around a non-spinning black hole, all the way down as the spin increases to 1.2 RG around our maximally spinning black hole. If the gas is going in the opposite direction to the black hole spin, though, if for whatever reason the accretion disk manages to get set up in the opposite direction to the spin of the black hole, it's actually harder to stay in orbit. So in this case, as the spin of the black hole increases, if you're trying to orbit against it, you can see how actually the innermost stable orbit increases if you're going in the opposite direction. But we normally expect, by conservation of angular momentum, our disk and our black hole to be spinning in the same direction. So we normally consider being on the blue curve here. But the idea here is that if we can measure the location of this innermost stable orbit, we can just refer to this curve, and that will tell us the spin of the black hole. And we do that with our iron K line. So this is that same image that I showed before, this ray-traced image of the inner accretion disk and the energy shifts of photons that are emitted from different radii. And you can see for a non-spinning black hole, because the innermost stable orbit is all the way out at 6 RG, there's this big gap in the middle of the disk. And we don't really see the strongest redshifts here. You can see there's a little bit of orange here, but there's not a really deep red color. If we increase the spin to 0.5, you can see we get closer to the black hole and the redshifts start to get stronger. And if we go all the way up to the maximum spin, you can see we've got this really small innermost stable orbit that's not far outside the event horizon with this extremely redshifted emission. And the way that will manifest itself in our spectrum is we'll get a broader and broader redshifted wing on our line. So if we can fit a model to the shape of our iron K line and determine how redshifted we're able to see these iron K line photons, then we can measure the innermost radius of the disk. And if we assume that the innermost radius of the disk is at the innermost stable orbit, then we can map that radius measurement onto the spin of our black hole. And we can do this for a whole nut sample of black holes. So this is a plot that Chris Reynolds put together from a review paper back in 2021. And this is for a number of supermassive black holes in AGN. And I realize I'm about to lose power, so we'll try and get through this. We've got the black hole mass on the x-axis, and then for each of these black holes, we've measured the spin of the black hole. But one thing, so does anyone want to say anything about sort of the spins of black holes in our universe from that plot? How do black holes in our universe seem to spin? Fast. Good, yes. So yes, it looks like we don't have black holes of all different spins in our universe. It looks like, at least in the AGN, most of the black holes we measure seem to be very rapidly spinning. So if we think that our black holes grow by the accretion of gas, if that gas always comes in from the same direction and the accretion disk is always orbiting in the same direction, we have to conserve the angular momentum of the gas that's coming in. So the angular momentum of the gas goes into the black hole. So that means if we keep accreting gas with its angular momentum pointing in the same direction, we will just keep increasing the spin of the black hole. So if our black holes grow by this ordered accretion from the same direction, we expect our black holes spin faster and faster and faster until they hit the maximum. But there is a caveat here. Yesterday, I talked about the efficiency, how much radiation we get out per material we put in. The radiative efficiency of a spinning black hole is much higher than a non-spinning black hole. A non-spinning black hole only releases about 6% of the energy through the accretion disk. A maximally spinning black hole can tap into about 40% of the energy. So this means rapidly spinning black holes, if they're in AGN, will often shine more brightly. So if we just point our telescope at the most interesting looking AGN and say, oh, we'll just look at the brightest ones, and the brightest ones are the easiest ones to do this experiment in, because you need a bright object to see the ion line, then we will tend to favor the rapidly spinning black holes, just because they're shining brightly and it's easier to detect the ion line. And you can kind of see that here as well. Our low spin black holes, or at least the moderately spinning black holes, you can see the error bar on the spin measurement is much larger than the error bar on the rapidly spinning black holes. And this is because those low spin black holes tend to be dimmer, less efficient, and it's harder to pick that ion line out of the spectrum. Yes. Oh, we'll get the microphone, yeah.
Can black holes slow down the rate that in which they spin through extraction of energy through the Blandford's-Naik mechanism, perhaps?
Yeah, exactly right. So actually, the Blandford's-Naik mechanism is extracting energy from the spin of the black hole. So over long periods of time, then you will be able to spin down the black hole if you do that. However, for a maximally spinning black hole, something like 40% of the total mc² energy of the black hole is actually in the rotation. And we have this concept in spinning black holes of the fundamental mass that we call the irreducible mass, and then the rotational mass. That's the fraction of the mass that's in the rotational energy. So for a 10 to the 7, 10 to the 8 solar mass black hole, 40% of that in the rotation times mc² is an enormous amount of energy. So on cosmological timescales, we don't really expect jets to spin down the black hole just because there is so much rotational energy in there. But yes, in theory, you would reduce the spin of the black hole. But if you've got an accretion disk coming in, that will bring angular momentum in with it. So if your quasar or radio galaxy is powered by an accretion disk, then you will bring more angular momentum in as well. So you'll be able to top up that spin. And this slide is just showing that we don't just do this experiment now. Oh, sorry, yes. Do we have the microphone at the front?
Yes, I can. Okay, I was just wondering if the low spinning black hole or the high spinning black holes, they are brighter.
Yes.
So how do we now compensate the low spinning black hole? Because this one outshines the other one. I was just wondering.
Yeah, exactly right. And it's a difficult thing to do. We can take that into account. So if we want to understand where black holes come from, we want to measure the spin distribution. So we want to plot a histogram of the number of black holes against their spin. So what we can do is, because we understand kind of the relationship between the spin and the telescope and the survey, how that biases the population. So in principle, what we can do is multiply the spin distribution measure by a selection function that then corrects for this.
Okay.
Yes.
And I will also exploit the darkness as
Sure.
now on the previous slide, I was seeing this in
Yes.
I was expecting a kind of linear relationship. Maybe the mass of the particle is needed, one will expect a spin increase on. Why is it that nothing of that?
Yeah. That's a really good question. We'll come to this at the end of the lecture. If you're tapping into that, something we actually really struggle to understand in the formation of particles. And one of the challenges we find is, in particular, if we look high redshift, so we look at things a long time ago in the universe, we actually see that there are massive black holes very early in the universe. That means these supermassive black holes must have grown very quickly. So it's likely what happened is that the black holes grew very quickly, and they all started spinning very rapidly. And then they kind of maxed out. So once those black holes get to that spin of sort of 0.9 net, they actually don't spin up anymore. They can accrete more material, but they won't gain any more angular momentum. Well, the black hole will essentially reach this maximum spin. And if we want to know more about that, there's subtle arguments as to what happens to that angular momentum, but we can talk about that later if anyone's interested. Do you have to
Share game.
suggest we, yeah. Zoom will get your okay, so I think Zoom's just getting out all that. So I probably shouldn't say too much of this into the area. If I can just sort of talk about a little bit of interesting practice. Here is so these 4, maybe 5 light sources here. 4 of them are the interesting ones. These are actually one single quasar. And what we're looking at here is what's called a gravitationally lensed quasar. This is called the Einstein quasar. This is one quasar that's at a redshift of about 1.5. Most of those black holes have kind of been the spot, and the least they're spinning, and with a redshift of 0.1 or even less. They're very low black holes. Because the nearby ones are much brighter, it's much easier to measure the spin. What's happening here is this quasar. There's a galaxy sitting on the line of sight. The gravitational field of that whole galaxy is bending on its quasar. This is called gravitational lensing. And that galaxy is acting like a cosmic magnifying glass. So what would normally be a faint quasar, we struggle to measure, is actually quite bright. And if we have the supreme angular resolution
around this galaxy, we get not one magnified image of the quasar, but 4. And the magnification means our quasar now becomes bright enough for Chandra to get a high quality spectrum. And what we can see is just like those nearby AGN, we can model the spectrum with a continuum, a power law, and then a broad ion K line in a reflection spectrum from the inner accretion disk. But for those of you who are paying close attention, you'll notice that ion K line is not at 6 keV. This is because this galaxy is at a redshift of 1.5. So we measure this, this ion K line at about 2 keV. And this is actually really good for Chandra because Chandra doesn't have great collecting area at 6 keV. So while it has great angular resolution, it's not very good at looking for ion K lines in the near universe. But the redshift of this quasar puts the ion K line right into the sweet spot of Chandra's sensitivity. So we can measure the ion K line, and we can measure the spin of the black hole, and we find that these high redshift quasars, so the Einstein cross at 1.5, and we can do this with quasars now all the way out to about redshift 2. There's some papers by Rubens Rees, Mark Reynolds, and Don Walton, showed that even these higher redshift quasars, in addition to the nearby CPET galaxies, also have very rapidly spinning black holes. So now we can look back in time in our universe and measure the black hole spins. So that's what we can do with X-ray reflection. What I'm going to do now is talk about a related technique called X-ray reverberation. And some of this will be familiar from what Diego was talking about earlier. Here we move from the spectrum into timing. So most of the AGN in which we get these strong iron K lines from the inner disk are nearby Seyfert galaxies. In fact, they're a particular class of Seyfert galaxies called the narrow line Seyfert 1s. We don't need to worry too much about exactly what a narrow line Seyfert 1 is, but these are radio quiet AGN that predominantly have bright coronae that are compact and close to the black hole that give us a strong reflection signal from the inner accretion disk. But another property these narrow line Seyfert 1 galaxies have, this is one of my favorites here. This is one called Wandswicki 1. You can see in Pan-STARRS, the kind of spiral galaxy there with the bright AGN in the center. And this is the light curve that we've collected with XMM-Newton in different observations between 2002 and 2020. And we can see that this X-ray emission is incredibly variable. Over time, we see this random variability. This is the broadband noise or the red noise that Diego was talking about. But then we also see these state changes. We see sometimes this AGN is in a bright state, sometimes it drops into a dim state. And we also see these really quite dramatic events like these sharp X-ray flares in this AGN. But this high degree of variability is extremely useful to us. So if we go back to our picture of reflection, we can imagine there's an X-ray that travels straight from the corona to us. So when the corona changes its brightness, we'll first of all see that change in brightness in the continuum component, the light path straight from the corona to us. We'll also get the reflection from the disk, but it takes time for those photons to go all the way down to the disk and all the way back up. And in a supermassive black hole, the light travel time from the corona to the disk, so this kind of 2, 3, 4 gravitational radius distance that it has to travel, that corresponds to millions of kilometers. So these are light travel times of tens to hundreds of seconds that we can measure in instruments such as XMM-Newton. So what we can do with XMM-Newton is we can plot a spectrum. And this spectrum isn't a typical spectrum of energy versus flux or energy versus count rate. It's energy versus time lag. And what this is showing is every time there's a change in brightness of our X-ray emission, how long does it take on average for each different energy to respond to that change in brightness? So what we find, so remember in our XMM-Newton spectrum, we had a continuum, and then we had a reflection that peaks at soft energies. We had the soft excess, the low energy reflection, and we had the broad iron K line at 6 keV, which means the continuum kind of sits in the middle of the soft excess and the iron K line. We find the energy bands that have the biggest contribution of the continuum emission respond at the earliest times. So these come in at the bottom of this plot. But then the energy bands in our spectrum that have the, I'll come to you in just a moment, that have the iron K line and the soft excess, because of that additional light travel time to the disk, the iron K line is delayed, and so is the soft excess. These photons tend to arrive later than those coming straight to us from the corona. And remember, we had a broad iron K line. We had that long red-shifted wing of the red-shifted emission from the inner disk. Because that inner disk is closer to the corona than the outer disk, we can also look here, and we can see that the red-shifted wing of the line, because it's closer to the corona, responds at an earlier time than the core of the iron K line that's coming from much larger radius in the disk. Yes, a question.
So my question is, like, what did you choose as the reference for this lag?
Good question. We'll come to that in a few slides' time, but the reference here is totally arbitrary. So all that matters is the relative arrival time of each band relative to the other. What we actually do is the relative band here is everything. So what we do is, so say for the so this data point at 6 keV, what we do is we measure that relative to everything else. So we take the full band and then we subtract the current band we're looking at. And we do that for each point. But how do we actually make these time lag measurements? And here, building off of Diego's lecture earlier, we're going to take a little diversion out of this kind of real space we live in, where we think about space and time. We're going to jump into Fourier space, where instead of thinking about things in terms of time, we're going to think about signals in terms of frequencies. So the way we do these measurements is, first of all, we're just going to do a very simple measurement. We're going to try and measure the time delay between the the soft reflected X-ray band that's highlighted in blue. So you can see here the reflection component is bigger than the continuum in the blue band. We're going to try and measure this time delay relative to the red band, which is dominated by the continuum. The way we do this, first of all, is we go to our XMM Newton data, is one of the best instruments for doing this. We can also do it with NuStar. We can kind of do it with Chandra, and we can certainly do this with NICER. This is timing type experiments are exactly what NICER is designed for. But we extract the light curves, but only in those specific energy bands. So these are the light curves of the red band dominated by continuum and the blue band dominated by reflection. And you can see that each of these light curves is kind of random. This is this broadband red noise type variability. So what we want to do is we want to try and measure the time delay of the blue band with respect to the red band. And by eye, that's kind of difficult to do. You can maybe try and line up some of these peaks with each other. But the problem here is that these light curves are random. It's very difficult to know which peak in one light curve corresponds to which in the other, except for where we've got the really big peaks. So what we do is we take the Fourier transform of this light curve. And the Fourier transform of a light curve has 2 bits of information in it. What we're doing is we're taking this random time series and we're building it up as the sum of different sine waves of different frequencies. And those frequencies actually have physical interpretations as well. The low frequency components correspond to the slowly varying processes in our X-ray emission. The high frequency Fourier components correspond to the rapid variations, the process that's driving the rapid variability. And what we do in our Fourier transform is for each of those sine wave components, we find its amplitude, so how strong that signal needs to be to build the signal we've got. But we also have the phase. The phase of the sine wave is whether we have to shift it left or right to match our signal. So we build up this random light curve as a sum of sine waves of different frequencies. We adjust the amplitude of each sine wave and we adjust the phase of each sine wave. And we can write down these Fourier transforms. If we write it down as a complex number, I have my H is my hard band in red, S is my soft band in blue. The Fourier transform of H is equal to the amplitude of the Fourier transform. So this first term here, this H magnitude term, is the amplitude of each frequency. But then each frequency also has a phase that I write down as an angle, e to the I theta for the hard band, e to the I phi for the soft band. And then I do a little bit of Fourier transform magic. I write down something I call the cross spectrum. And what that means is I multiply these 2 Fourier transforms together. But before I multiply them together, I take the complex conjugate of one of them. And what the complex conjugate does is it turns the positive phase into a negative phase. So if I complex conjugate the H here, we turn theta into minus theta. So now our cross spectrum we multiply together the 2 amplitudes. So the amplitude is essentially the power spectrum of each of these time series. So the magnitude of the cross spectrum is just the magnitude of H times the magnitude of S. But then my phase of my cross spectrum now has this theta minus phi in it. It is the difference in phase of the 2 light curves. So the phase is expressing the delay between the sine waves in terms of an angle. But then we can easily turn an angle, if it's a sine wave, into a time delay just by dividing this, the argument of this cross spectrum. So this theta minus phi term here is the phase delay. If we just divide it by 2 pi times the frequency, we turn the phase lag into a time lag. But what's critical here is that we're measuring this time lag for every single Fourier component that makes up our light curve. So we can measure different time lags in the fast components of the variability and in the slow components of the variability. So what does this actually look like in practice? So these are the light curves of another AGN that I quite like working on. This is called Aracelian 564. And if we do this calculation based on these two light curves, we find that the time lag, the time delay between the two light curves in the different frequency Fourier components has a graph that looks like this. By convention, a positive time lag means the hard band, here our continuum, is delayed. A negative time lag means that the soft band is delayed. And if we look at our spectrum, it's the soft band that's the reflection. So our reverberation signal, where the reflection is delayed because of the light travel time, that is the negative part of this graph. So in the frequency range, in the components of our variability at these time scales or these frequencies, where the time delay is negative, this is where we're measuring the reverberation signal. And just how negative this part of the plot gets, that is the magnitude of our time delay. And we can interpret that. We need to think a little carefully, but we can kind of interpret that as the light travel time between the corona and the disk. I just wanted to illustrate exactly what this plot means. So what we're doing with the Fourier transform is we're separating into the high and the low frequency components. So what I can do is I can take our light curves here and I can pull out just the low frequency and just the high frequency components. So you can see in this Fourier transform, here's the low frequencies. Makes sense, right? This is the slow variation. And you can see how the big peaks in our light curve correspond to the peaks in the low frequencies. And then we add this to the high frequency components, and you can see the high frequencies are varying much more rapidly. In our low frequency range, the red band, the continuum, is behind the blue band. And that we can see this. If I zoom in here, you can see that the red peak is later than the blue peak. And we can see that all the way across this light curve. The red peak in the low frequencies is delayed. But then at high frequencies, I'm just going to zoom in so we can see it more clearly. We can see here that now the blue peaks are delayed with respect to the red peak. So you can see there the blue comes later, the blue comes later, the blue comes later. So that's just visualizing what we mean by this lag versus frequency plot. And now what we can do is we can take this plot. Oh, yes. Do we have the microphone?
So in the previous plot, isn't it like the opposite is there? Like the blue is lagging red in the upper pan, the previous slide.
Oh, yes. So in the
like
blue region of the...
In the middle panel, I think blue is lagging red.
So most of the time, so remember these are random variations. This isn't a sine wave. This is a random red noise light curve. Most of the time, the red is lagging the blue. The red, you can see there, the red peak is later than the blue peak. You do get some time periods where it swaps round, that here you can see the blue is a little bit later. Because it is a random noise process. The blue sometimes comes later, but on average over all the peaks, the red is delayed with respect to the blue in the middle panel. So if you look at sort of this big peak here, you can see the red peaks come after the blue peaks. Does that make sense?
I think at a particular time, so suppose, okay, so the last peak, the very last peak. So here, blue is lagging red.
No, the red is after the blue here. You see the solid red line is to the right of the dashed blue line.
I mean, red has appeared first, then the peak of red is first, then the blue is appearing. The peak of blue is coming later than the red.
No, the peak of the red here is. Yeah, so you can see if you look at the rise here, the way the rise from that minimum to that maximum, you can see the red is to the right of the blue. Yep. Yes.
So I have a question that when you pick two bands, right? Can you go back to the spectrum page?
Yes.
So here, yeah, the two bands you have chosen, that the blue and the red, right?
Yes.
So in the blue, we can see that there are contribution not only from the reflection, but the continuum also. So my question is, do you usually subtract, or is there any way?
Well spotted. So we never subtract. Subtracting is evil. That's taking signals out and assuming we know what the signal is. So, but you're exactly right. Both our bands are contaminated by the opposite process. So what that means is actually our blue band will have some early arriving signal from the continuum. So on average, the time delay will be shorter than it should be. And likewise, our red band has contamination from delayed signal. And this is something we call dilution. So in reality, the time delay is something like this. These signals arrive a long time apart. But this contamination, this dilution, means the average time lag is shorter. But then if we know the spectral model, if we can fit a model to the spectrum and we know what the contribution is at each band, then we can model all of this simultaneously, and we can actually account for that when we do the measurement of the corona.
But when you calculate lag, you only take the bands, you don't.
Correct, yes. So what we do is we let the data speak for itself, and we calculate the lag just from the data. But then we have to fold that into the model when we interpret the data. Because the danger of subtracting light curves here is you don't really know, because it's a random noise process. In addition to Poisson noise, you don't know what the true signals are. So you'll always bias in some way if you do a subtraction. So then what we can do is, now we know what frequency range our reverberation appears in. Instead of just extracting two light curves, we can extract lots of light curves in narrow energy bands. And then for each of these light curves, we can do the same calculation of time lag. And instead of plotting the time lag at every single Fourier frequency, we bin our Fourier frequencies and we calculate the average time lag over that whole range of frequencies where the plot is negative. And then we can see this arrival time versus energy spectrum. And here we see that classic shape of the reflection spectrum that I showed earlier, with the iron K line, with its red wing, and the delayed soft excess. But what's going on at low frequencies? How is the reflection arriving ahead of the continuum at low frequencies? Well, it's not. But this goes right back to the question here, is that these bands aren't pure reflection and continuum. What we can do is we can do the same experiment. We can plot this time lag versus energy over that low frequency range. And here we don't see a reflection spectrum at all. Here we see what we call a hard lag, where the hard X-rays, the high energy X-rays, always respond later than the soft lag, the low frequency X-rays. And this isn't reflection versus continuum at all here. This is the contamination of the continuum in the blue band interacting with the continuum in the red band. And we can understand this picture if we have a corona that's not a point source, if we have an extended corona, a corona that's hotter in the middle than on the edge. So what's going to happen is our disk is going to be fluctuating all the time. Materials are accreting through the disk. We've got clumps, we've got overdensities, we've got underdensities. We have our turbulent magnetic field as well. We've got high energy areas, we've got low energy areas. And with the accretion, things are propagating inwards. So if every time our signal varies, the variation starts out at large radius in the cool corona, and then it propagates inwards and then reaches the hot inner part of the corona later, then we expect the high energy X-rays that mostly come from the hotter part of the corona to always respond later. But this is a slow process. Reverberation, this is signals traveling at the speed of light. This is X-rays going from the corona to the disk at the speed of light. So we see this in the high frequency Fourier components. This propagation process doesn't necessarily travel at the speed of light. If this is material moving through the accretion disk, or it's things accreting or traveling through the magnetic field, that will travel more slowly. So this propagation happens in the low frequency components, which is why we see this turnaround here. But when we measure reverberation, this is why we do this in the Fourier domain, so that we can filter out the high frequency and the low frequency processes, and we can analyze the high and the low frequencies separately. Now, if any of you want to get your hands dirty with this, we call this spectral timing. So timing is this idea of light curve analysis, Fourier analysis. Spectral means we're doing things as a function of X-ray energy. And spectral timing is when we join this together. We're combining the timing information with the spectral information. Methods have been developed in the last couple of years. This is much more recent than a lot of software like HereSoc and the Chronos package that's in your HereSoft install. So we don't use those tools like that. We have some specialized tools that we've been developing more recently. The most comprehensive is this tool called Stingray. This is written fundamentally in Python, and it lets you do all manner of light curve analysis, Fourier analysis. You can calculate these cross spectra, these lag spectra. You can do pulsar timing, phase resolved analysis, all manner of different things in light curves. And then another tool is one I've been working on myself, and this is a piece of software called PyLag that isn't as fully featured as Stingray, but it's more focused on this lag analysis, on this reverberation analysis. So this again all runs in Python, and you can put together some nice Jupyter notebooks, but it's got some functions and some classes that automate a lot of this light curve, cross spectrum, power spectrum, lag spectrum analysis. And if you're interested in doing anything with those, do let us know. But I would just, I'll come to Jeremy in a moment, but one thing I'll say is if you want to do AGN timing though, in missions like NuSTAR and NISA, where we're in low Earth orbit and there's gaps in the observation, do please come and talk to us, because if you try and do a Fourier transform across a light curve that's got gaps in it, you can make a bit of a mess. The gaps make a total mess of the Fourier transform, so we need to be a little bit more careful in how we analyze that. Jeremy.
Yeah, just curious what the kind of typical runtimes for these reverberation studies are on like a laptop, for instance. Is it doable, or do you use?
Absolutely. So these, so all of this cross spectrum and lag spectrum analysis, it's all based on fast Fourier transforms, and often will run in seconds or less. The slow bit actually is getting your light curves. So particularly with NuSTAR and with XMM Newton, we use corrected light curves, and the tasks that do the exposure correction on the light curve tend to be the slowest part of this analysis. But once you've got your light curves, these Fourier analysis are nice, fast things that you can do the analysis, and you can play with things, you can try different things, and really have the results coming up in real time. And then what we can do, I'll come back to you in a moment. What we can do is we can then measure these time lags. So here we have that soft X-ray time lag. So this is between the soft X-ray reflection and the continuum, 0.3 to 1 versus 1 to 4 keV. And we can measure the ion K time lag. So this is the 4 to 7 keV ion line versus the 1 to 4 continuum. And these are samples that were put together by Barbara DeMarco for the soft lags and Erin Kara for the ion K lags. We can plot as a function of black hole mass the time lag we measure in different black holes. And we see this nice correlation. The time lag approximately scales with the mass of the black hole. And remembering that our characteristic distance in the black hole is GM around the black hole is GM over C squared. The scaling of our lag with mass tells us this is really probing some fundamental scale around the black hole. And if we know the gravitational radius, gm over c squared, gm over c cubed is the light travel time over a gravitational radius. So what we can do is we can just compare the time lags we measure to the light travel time over different numbers of Rg. And we find that these light travel times correspond to really quite small distances around the black hole. So this is telling us that our corona is often at a height above the accretion disk of somewhere between 1, 2 Rg and no more than 10 Rg above the black hole and above the accretion disk. So our coronae here really are quite compact.
Is it not telling us about like corona is not on the height, but around the black hole?
Yes, that's a good question. So yes. So the fundamental measurement we're measuring here is the vertical height of the corona above the accretion disk. And we're finding something that's 1 gravitational radius above the accretion disk to 10 gravitational radii above the accretion disk. So for the shortest time lags, this is maybe telling us that it really is quite close to the disk. And then for the ones, if it's a lamppost, that will need to be a couple of gravitational radii up. But there's a couple of caveats in here. So these time lags, first of all, are just the raw time lags. But we do need to account for that spectral dilution. So actually the real light travel distance can be a factor. So that the spectral dilution often gives us a factor of about 1/2. So often these intrinsic time lags, we need to, depending on the exact spectrum in the object, we need to about double those. So the 1 Rg is maybe 2 Rg. So you can maybe fit it in above the black hole. But whatever it is, it's small and it's compact. And just as kind of a summary here, so we have our INK line. We measure the broad line, that's giving us different Doppler shifts, different gravitational redshifts. The Doppler and gravitational shift vary as a function of location on the disk. So if we measure an INK line and we measure the energy shift of a photon, we can begin to piece together whereabouts on the 2-dimensional disk surface it came from. But now if we add the time delay of that photon, we then get how far away that part of the disk is from the piece of the corona that illuminated it. And our dream here is, as we move towards bigger missions, bigger X-ray telescopes, is we'll have enough photons to do this spectral timing at high resolution, where we can start to build up this 3-dimensional map of the accretion disk and how the corona is arranged around it. And the way we do this is with some theoretical models, and this is something I've worked on quite a lot. And if anyone is interested in how to do this, I'd be more than happy to talk. But essentially, we can use something called general relativistic ray tracing, where we calculate the paths that photons take in the curved space-time around our spinning black holes. We can start with a corona. We can trace the rays down to the disk, measure how much reflection we expect from different parts of the disk. We can then, in that little patch of the disk that we've just illuminated with an X-ray, we can run Javier Garcia's silver code, and we can predict what the reflection spectrum looks like from that part of the disk. And then we can run this ray tracing again, send those reflected rays from the disk out to our telescope. And then once these rays arrive at our telescope, then we can simulate the spectrum we expect and the time lags we expect. And then we can compare that to our data to see what's going on. And kind of what's going on here is, here's a cartoon of our accretion disk. We have a flare that goes off in the corona, and then as a function of time after that flare, we're seeing the reflection appear from different parts of the disk. And these different parts of the disk just illuminate at different times, depending on the total light travel time from the corona to the disk to us. So you can see the bit of the disk nearest to us responds first. And then what's cool is we see this ring, you see that inner ring detach, and we get this really slowly moving ring going in towards the inner accretion disk. That's because the photons that have to climb out of that strong gravitational field around the black hole get delayed. So we can actually see how the photons coming from closest to the black hole not only get redshifted, but their passage to us gets delayed. And of course, we can use all of these techniques to create a map of our corona. So one thing we can do is we can just take the shape of our iron K line. We know what the energy shifts are from different parts of the disk. We know the Doppler shifts and the gravitational redshifts. So we can say, if this is the shape of the redshifted wing of our line, this is how much reflection we need to get from different parts of the disk. So what we can do is we can plot reflected flux, we call it emissivity, versus radius on the disk, reconstructed from the shape of the iron K line. And we can see how that strong light bending pulls rays to the inner disk and how brightly illuminated the inner accretion disk is. And by looking at how flat the illumination of the disk is, so if the corona is running over the top of the disk, you'll get uniform illumination underneath it. By measuring over how big a range we see uniform illumination before it starts falling off on the outer disk, we can measure how wide the corona is over the disk. And we can start to see that the corona is no more than maybe 5 to 10 gravitational radii in radius over the surface of the accretion disk. And then maybe a couple of gravitational radii in height that we measured from the time delay. And what we're kind of doing here is kind of like a fake event horizon telescope here. We're reconstructing the flux as a function of radius on the accretion disk. So this is actually an image of the disk we reconstructed in an AGN called Markarian 335, just based on the reflection of the iron K line. And of course, we can model the time delay again. I've said this already, but here's the delayed response of the iron K line and the soft excess, and they're delayed with respect to the energy band that's most strongly dominated by the continuum. We can see in this theoretical model as well how the redshifted line from the inner part of the disk, because it's closer to the corona, has a shorter response time than the iron K line from the outer disk. And the simplest interpretation here is the height of the iron line lag and the soft X-ray lag just tells us the scale height of the corona above the disk. We can also use a simple relativistic beaming argument to learn more about our corona. So if we just have a corona that's emitting isotropically in all directions equal X-rays on an infinitely big accretion disk, you expect 50% of the X-rays emitted by the corona to go up, away from the disk, so we see that as continuum, 50% of those rays to go down and hit the disk. So if we divide the reflected flux by the continuum flux to create something we call a reflection fraction, in classical physics, isotropic light above an infinite disk, we expect 1. If we add gravitational light bending for a compact corona that's close to a black hole, we pull many more photons down to the inner disk, so we can get R greater than 1. The most extreme we've measured is R between 5 and 10, when our AGN drop into really low luminosity states and the corona shrinks to this really small volume around the black hole. But sometimes we measure R less than 1. We measure more continuum than reflection. And that can happen if our corona is being ejected away from the black hole. So imagine a corona that's maybe part of a jet, or maybe a small scale thing that's trying to become a jet, but not reaching those large scales we see in the radio galaxy. In this case, if we have motion of the corona at 10%, 20%, 30% the speed of light, the beaming sends the radiation away from the disk, so we see more continuum than reflection. So here we can measure not just the location of the corona, but we can start to understand the velocity of the corona. And if you want to know more about that, a former student of mine, Adam Gonzalez, wrote a really nice paper running through all these models and explaining how this motion of the corona affects what we see. And we can put all of these observations together to kind of put together this picture of the corona. So what we see in our measurements is we have our reverberation that we see in the rapid components of the variability coming from this compact core of the corona that looks a little bit like a failed jet. But then we also have this slowly varying component of our X-ray emission that looks like it's associated with magnetic fields on the accretion disk. And there's one last measurement we can actually do of the size of the corona. And this is a paper from Dye et al. Back in 2010. And this was looking at these gravitationally lensed quasars. When we have gravitational lensing, the galaxy that's moving doing the lensing isn't a pure magnifying glass. It's a galaxy that's full of stars, and those stars are moving. So the lens is always changing. So that means the magnification of our quasar sometimes goes up, sometimes it goes down as the stars move in the lensing galaxy. This is called microlensing. Now, big objects aren't affected really by microlensing. So if something is very big, you will only see very small variations as the stars in the lens move. But if something is very compact, you will see big amplitude variations with the microlensing. And what we can actually do is we can use microlensing measurements, and Dye et al. And Chartas et al. Have done this. We can turn this microlensing variation into a size. And here we can see that the size of our corona is smaller than 6 Rg, so consistent with what we're finding with the X-ray reflection measurements. And just for conversion here, helpfully they put distances around a supermassive black hole in centimeters, go figure. 10 to the 13 centimeters is about a gravitational radius here in this quasar at 10 to the 8 solar masses. And our AGN are extremely variable objects. This is the light curve from SWIFT of Markarian 335, and we can see just how crazy the X-ray and the UV variation is here. We see it go through bright states and dim states, and occasionally we get these bright flares that get emitted from the accretion from the corona. And the same in that AGN I talked about earlier, Wiki 1. In 2020, we saw these 2 really short, sharp, bright flares towards the end of the observation. And what we can do is use all of these techniques at different times of our observation to measure how the properties of the corona change. We can see changes in the photon index that tell us about the energetics of the corona. We can see changes in the cutoff energy we measure with NuSTAR that probes the temperature of the corona. We can measure that reflection fraction that tells us about how fast the corona is being ejected away from the disk. And we can see the reflection fraction drops precipitously during the bright flares, hinting that this corona is being launched away from the black hole during these X-ray flares. And then we can also kind of measure the extent of the corona, but in this object, the error bars are quite big, so we can't really say a lot here. It looks like the corona expands as well. But we kind of get this picture emerging of during these bright X-ray flares, this corona gets gathered up, it gets launched away from the black hole at maybe 20%, 30% the speed of light, sometimes even higher, almost like this black hole is trying to launch a jet, but it fails. And this corona gets ejected, we see the corona get launched away, and then what's left then collapses back down to a small region around the black hole. So the one last question I want to talk about in maybe like 3 minutes is, how did supermassive black holes form, and how can we start to tackle this fundamental question from the observations that we've already talked about? Well, what we need to form supermassive black holes is we first of all need some seeds. We need some small black holes that are going to grow. And we don't know where these seeds came from. Either we had big clouds of gas left over in the centers of galaxies that just collapsed directly, or we have an early generation of massive stars in the centers of galaxies that come to the end of their lives and form black holes, and then they merge. And this forms the seeds of our supermassive black holes in galaxies. The direct collapse is quite hard to do. So in this case, we don't expect all the small galaxies to have black holes. But if it's these early stars, then we do expect the small galaxies to all have supermassive black holes in the center. So if we can measure how many dwarf galaxies have black holes and what the mass distribution of those black holes is, we can start to distinguish these 2 scenarios. But then these black holes grow. They can either accrete, and here we expect the angular momentum to be conserved, and we expect to spin up those black holes. And then, or these galaxies will merge with each other. And then we expect the black holes to go to the center of the new galaxy. And then we expect the black holes to spiral into each other and merge as well. Stable accretion from the same direction will by conservation of angular momentum will spin up our black holes. But chaotic accretion from random directions and mergers of black holes coming in with different spins will tend to spin down our black holes. So as well as measuring the distribution of black holes among dwarf galaxies and measuring their mass distribution, by measuring their spin distribution, we can also understand how they grew. Was it by accretion or was it via these mergers? I'll skip measuring black hole masses for now, but this is mostly optical. But if anyone wants to know more, there's information in the slide, or we can talk about this later. But I'll show that this is that same plot we had before of the spin of the sample of supermassive black holes, plus the low mass supermassive black holes that tend to be found in dwarf galaxies. So here's that black hole mass versus spin. And what we can do here, this is a plot put together by Javier Garcia's team, in particular, Asia Petroska put together this beautiful plot of the spin measurements we have, along with some spin predictions of black holes from cosmological simulations. So you can see here how we can compare the theory to the spins we measure of black holes, as well as the mass of the black holes we measure. And as we do this for more and more black holes, not only in the local universe, but looking back at higher redshift, we can really start to understand the formation pathway. And this is an area of science that we're really hoping to tackle with the next generation of X-ray observatories, including Athena and also some of the probe class missions we're working on in the US at the moment, really going after the spins of black holes outside the local universe and looking back to higher redshift. So here's just my summary for today. Reflection and these reverberation measurements let us probe what's happening right outside the event horizon of these black holes. We can measure the spin of the black hole. We can also measure the mass of the black hole. And we can start to understand the structure of this corona. We can make real observations of the nature of the corona, the location of the corona, and how it varies in time. And we hope fundamentally by measuring the mass and the spin and the properties of these black holes, we can start to understand where the supermassive black holes in the universe came from, which is obviously important in understanding the growth of galaxies and the growth of cosmic structure as we understand it. So thank you, everyone. I'm happy to take questions, but yeah.
Hi. Does Relzil or silver always assume a Lampos geometry for the corona?
So there's different ways you can use Relzil. So silver itself is just the reflection from a little piece of plasma, so just one patch of the disk. And then it's Relzil that takes that and combines it with the Doppler shifts and the gravitational redshifts. We have different ways that we can use Relzil. In one mode, we can use a lamppost geometry where we assume it's an infinitesimal point on the axis of spin of the black hole, and we can vary the height. Or there's also a more model-independent approach where we don't model the corona, but what we do is we model that emissivity of the accretion disk as a power law or a broken power law. And in that mode, then we're not tied to any particular model of the corona, but we can measure the emissivity and then compare that to models of the corona. And that lets us exploit different geometries like extended coronae or moving coronae. Yes.
Yes. So one question that I had, the structure of the corona. So what you're saying is it's a compact core, and then you have a vertically varying structure as well.
Yes.
So so why exactly would can you explain why exactly would the lag be indicative only of the vertical variation and not any other radial variation?
So it kind of is sensitive to the radial extent, but not much. So what we're measuring here is, so that the simplest measurement you can make is just a one-time lag number. We say on average, this is the time delay. And if you run models of different coronae, all you're measuring there is the distance between the corona and the disk. So if you have a corona that's compact over the inner disk at some height, maybe 2 gravitational radii, you measure the time delay for 2 gravitational radii. If you then stretch that corona at the same height, but then the average light travel time to the disk is still only 2 gravitational radii. So to first order, you're only sensitive to the vertical height, just the distance the light has to travel. When you put in the spectrum and you measure the time delay at each point in the spectrum, that's when you become more sensitive to the radial shape and the vertical extent. And I didn't talk about the details today, but that's how we get this picture of the two-component corona, is when we look at the higher order energy variation of the time lag.
Thank you.
Yes.
Okay, I'll ask while I've got the mic. I was wondering about power density spectra, and like in accretion disks, I'm familiar with, how you can sort of look at the stochastic processes, determine the nature of the turbulence spectrum, turnover frequencies, all of that sort of stuff. Is this something that you can do with the corona as well, or not?
It is, yes. So Ian McCarty wrote some papers back in 2006 and 2007 using RXTE data. It's something we've struggled to do since RXTE, just because RXTE monitoring gave us the power spectrum and the light curves on long time scales that we can't do with observatories like XMM, just because we can't use XMM to stare at the same quasar for a year. But what we find is that actually, yes, you do measure a break frequency in the power spectrum. It goes from approximately 1/f squared at high frequency to 1/f at low frequency. And that break frequency indicates it actually scales with both the mass and the luminosity of the black hole. So it's not quite a simple mass relationship to mass that then we can say, okay, this is the radius in the disk that all the variation's coming from. But what we can do is we can use empirical relations, mass, luminosity, break frequency, and then that will give us a handle on things like the mass.
Yes, Dan, I'm just wondering whether there could be maximum mass limit to these supermassive black holes. And what if the situation comes when two supermassive black holes merge? What would happen?
So what happens when two supermassive black holes merge? In fact, this is a most interesting question actually from the gravitational wave point of view. So when two supermassive black holes merge, what we normally think they do is they end up in a binary orbit with each other. So you have these two black holes going around in orbit, and as they're in orbit, they're radiating energy out as gravitational waves, and that causes the orbit to decay. And then the orbit gets faster and faster, the decay gets faster and faster. And then just like in the mergers that were seen with LIGO, we get this gravitational wave event as the two black holes collide. And then you get this ring down, it's called this big ringing of intense gravitational waves. And this is something actually the LISA mission hopes to measure. LIGO can't get to the low frequencies that we need to measure supermassive black holes. But then when the two supermassive black holes merge, what you get is just a bigger supermassive black hole. And from an astrophysical point of view, there's not really a fundamental limit that we expect to reach as to how big a black hole can get. Kind of the limit we normally hit is actually how big can a black hole grow over the time it's had in the universe. And this is a bit of a challenge actually theoretically. We find black holes that are much too big at much too high a redshift. But there's a limit to how much gas you can get in, and because the universe has a finite age, that kind of sets the limit on the size of the black holes we see. But then when two supermassive black holes merge, you form a bigger supermassive black hole it's not quite the mass of the two added together, because you lose mass when the gravitational waves radiate, but essentially, yeah, you just form bigger supermassive black holes.
Okay, so you were talking about the corona and accretion disk, but I'm quite interested on the jet and the accretion disk. Like on the jet, we can see like a jet knot inside. So I was wondering, like, can we use the same models? Like if we are thinking about the jet knots and the accretion disk, like can we use the same models as the corona and the accretion disk? Or do I need to put like any parameters such as the distance? Because we know that the corona is quite near the black hole, but the jet knot, we can see it farther.
Yeah, that's a good question. So normally we think of the jet knots as being separate to the corona. Because a really interesting question is how do jets work? And if we can understand how those jet knots get launched, And if we think of the corona as being all the way down at the bottom of the jet, if we could observe simultaneously the inner accretion disk, the corona, and the jet knots getting launched, that would tell us really exciting things about how jets work. I mean, there's a really good paper by actually Anne Lofink in 2013, was studying jet knots versus the X-ray spectrum of a radio galaxy called 3C120, and I highly recommend looking at that paper. But yes, I think normally the jet knots in the spectrum, if we're thinking about the X-ray emission coming from those, we don't, by the time we see the jet knot in the radio emission, it's large distances away from the black hole. It's hundreds of gravitational radii plus. So that means we don't really expect that to really significantly illuminate the accretion disk, just because it's so far away. So for that purpose, we can consider the jet knot as being a separate emission component to kind of the X-ray source and the reflection.
Thank you.
Not to discourage, you can have discussion during lunchtime. Let's thanks again.